Welcome to this training video on real-world machine learning use cases. Machine learning is now an integral part of many applications, ranging from medical diagnosis to finding friends on social media networks. We will explore several foundational and advanced examples of how ML solves complex problems today. Let's get started. Machine learning, or ML, is a field that sits at the intersection of statistics, artificial intelligence, and computer science. Its core purpose is extracting knowledge from vast amounts of data. Instead of relying on hand-coded rules, ML systems automatically find patterns and make decisions based on past experience. This ability to generalize from known examples is what automates many decision-making processes. Think about when Netflix suggests a movie or Amazon recommends a product. These systems use ML algorithms at their core to personalize your experience. ML systems are used by companies to solve complex problems ranging from medical treatment to finding friends on social networks. Understanding ML applications helps set the stage for our training. What we have learned here is that ML is about learning patterns from data to automate decisions, which is known as predictive analytics. This simple flow illustrates the core process of machine learning. We start with raw data input, which is processed by an ML algorithm. The algorithm works to perform knowledge extraction by identifying complex patterns. Finally, this learned knowledge allows the system to generate a prediction or make a decision on new, unseen data. This foundational capability enables the widespread use of ML applications in the real world. We will now move on to look at specific types of ML applications, starting with supervised learning, where the output is known. Our first major category is supervised learning. This is where a teacher provides supervision to the algorithm in the form of desired outputs for each example it learns from. If your task can be structured this way, ML can likely solve it. Binary classification is the simplest form of supervised learning, where the outcome is one of two choices. Spam detection is a perfect real-world example. Historically, spam filters used hand-coded if and else rules. However, machine learning allows the system to receive many emails, inputs, along with their status, desired output, spam or not spam, and automatically learn the patterns that define spam. The model can then predict if a new email is spam without human intervention. This is often much more robust than manually crafting rules. What we have learned is that binary classification, like spam detection, predicts one of two defined outcomes using labeled input data. Next, we look at how this generalizes to more complex outcomes. Building upon binary classification, many real-world problems require multi-class classification, which means predicting one of several options. For example, classifying handwritten zip codes means predicting which of the 10 digits, 0 through 9, the writing represents. A significant real-world challenge ML solves is complex image recognition, such as face detection. Humans struggle to write rules defining a face based on pixels because computers perceive images differently than we do. By providing the algorithm with a large collection of images of faces, the algorithm determines the necessary characteristics itself. In healthcare, ML systems can help diagnose diseases like cancer or diabetes by classifying complex data patterns. What we have learned is that ML excels at complex classification, managing tasks where outputs are one of many possibilities, like identifying faces or medical conditions. We will now explore predicting numbers instead of categories. We demonstrate a complex classification problem like recognizing multiple objects in an image. The image input is initially processed through feature extraction, where relevant properties are quantified. This structured data is fed into the ML multi-class classifier. If the system is trying to identify various items, the classes could be output object 1, output object 2, or output object n. This highlights ML's strength in identifying complex patterns in visual data, a task infeasible for traditional, rule-based software. Remember that successful ML relies on effective feature representation when using supervised learning techniques. While classification predicts a category or class, regression predicts a continuous numeric outcome. Regression is used whenever we want to predict a certain outcome from a given input, and we have training examples of input and output pairs. For instance, predicting house prices or forecasting time series data like stock values or RAM prices uses regression algorithms. Instead of classifying a house into a type, regression predicts the exact numeric price. When predicting complex real-world continuous values like flight prices, feature engineering using expert knowledge is crucial. For example, explicitly adding a feature that indicates if a flight is near a holiday helps the model predict price surges, something hard to learn just from the date. What we have learned is that regression focuses on predicting numeric values, making it vital for economic forecasting and pricing models. Now let's explore learning when there are no known outputs. This diagram shows the process of using ML for forecasting or pricing, a regression task. Historical price data is processed, often requiring feature engineering to incorporate relevant variables like house size or holiday dates. This refined data trains the regression model. The ultimate output is a prediction, continuous numeric value, such as a dollar amount or a future stock value. Regression differs from classification as the output is fluid and falls along a continuous scale. This is achieved using supervised learning based on past examples where the correct value was known. Now we move to unsupervised learning. Here, the algorithm receives only input data, without any predefined outputs or labels. While very useful, unsupervised methods are generally harder to evaluate and interpret. A key use case is clustering, where the goal is to group data points based on similarities. For a business, this could mean segmenting customers to understand their purchasing behavior and target promotions. Another application is topic modeling. If you have thousands of documents, you might want to find prevalent themes within them. Since you don't know the topics, or the number of topics beforehand, there is no known output, making this an unsupervised problem. What we have learned is that unsupervised learning is critical for discovering underlying structures and patterns in unlabeled data, such as finding customer groups or summarizing vast text collections. Next, we explore advanced applications that use text data in machine learning. This flow illustrates unsupervised learning, starting with unlabeled data input. This data is processed by a clustering or topic model algorithm. The output is discovered patterns or groups, such as different customer segments. For example, the algorithm might reveal a group of frequent shoppers and another group of low-engagement users. The goal is pattern recognition and grouping data points that share similar attributes. Critically, unlike supervised learning, no labels are provided to the algorithm during training, making it hard to evaluate performance directly. Many real-world applications involve text data, which presents unique challenges because it is stored as variable-length strings, not numeric features. NLP is the discipline that handles this, by processing steps to convert strings into a numeric representation that ML models can handle. A popular use case is sentiment analysis, where ML determines the intent or feeling behind a piece of text, like a customer complaint or a movie review. To use text in ML, we must convert it into a numeric format. The bag of words method does this by counting how often each unique word appears in a document. This creates a large feature vector where the order of the words in the original text is completely ignored. For tasks like sentiment analysis, linear models such as logistic regression often work best on this high-dimensional, sparse text data. What we have learned is that NLP transforms complex text data, often using methods like bag of words, to enable applications such as automated sentiment classification. Next, we look at applications that involve even greater complexity: deep learning. We illustrate the text classification workflow using sentiment analysis. Input text, like a customer review, is fed into the processing step. This step converts the string data into a numeric feature vector, often using the bag of words method, which creates a sparse vector of word counts. This vector is then input into the ML model, typically a classifier. The model returns the output sentiment, classifying the text as positive or negative. The conversion of text into a numeric vector is necessary because ML algorithms usually require input data to be numerical. We must ensure we select the best algorithm for this type of sparse, high-dimensional data. Neural networks, often called deep learning, can build highly complex models and are particularly effective for large datasets. These algorithms are essential for problems that are difficult for computers to solve but simple for humans, like recognizing a cat in a picture. Deep learning has enabled massive success in areas like automatically translating languages, as seen with Google Translate. A major, high-stakes application is object recognition for self-driving cars. These systems must instantly analyze incoming visual data to correctly identify objects, such as pedestrians preparing to step into the vehicle's path. If the model is too slow, it's useless. ML systems must achieve inference speeds acceptable to end users, often in milliseconds. What we have learned is that deep learning tackles high-complexity, high-stakes tasks, enabling modern technology like instant translation and autonomous vehicles. Finally, we contextualize ML within the larger production ecosystem. Here, we see an example of deep learning in action for object recognition. Raw sensor data from the vehicle, such as camera feeds, is fed into a complex deep neural network. The network processes layers of complex patterns. The system then produces a prediction or action, such as identifying an object or determining trajectory. Speed is critical here, as inference latency must be extremely low for real-time systems like self-driving cars. Deep learning is suitable here due to the large number of inputs, pixels, and the complex patterns involved. We must understand that the ML algorithm itself is just one component. In the real world, ML solutions are part of a greater, continuous process to solve a problem. An ML system includes not just the model, but also the business requirements, the data stack, deployment, monitoring, and infrastructure. This development process is highly iterative, meaning you constantly loop through steps like gathering data, developing the model, deploying it, monitoring performance, and refining the business goal. Monitoring is essential because ML systems, unlike traditional software, can fail silently. They might still run, but their predictions might be garbage due to shifting data distributions. Therefore, focusing solely on complex algorithms without considering the entire iterative system, including data quality and monitoring, is a common path to project failure. What we have learned is that production ML requires a holistic system view, emphasizing iterative development and continuous monitoring. This final diagram represents the iterative process for developing an ML system in production. The cycle starts with project scoping, defining objectives and constraints. It flows to data engineering, where data is prepared. Next is model development, where algorithms are trained. Deployment makes the model live. Critically, monitoring continuously checks performance. Finally, business analysis uses results to refine objectives, restarting the cycle. The process constantly cycles, because real-world data is dynamic and requirements change. This ensures the ML system remains reliable and adaptable over time.